name is Andrew Gross, and I work at Dassault System SolidWorks. And I was invited by Ashley to come and do a short presentation for you all on SolidWorks simulation. More specifically, um, it's our topology optimization tool, which is pretty cool. I have presented at the Phoenix user group many times over the years, although it has been a few years since I've been there, but many times live, few times I've presented virtually, but yeah, not since 2020. I think last time I was there was probably 2019. So it's really cool to get back in and see everybody. Um, so a little bit about me and my background. Like I said, I've worked at SolidWorks for about 10 years now. I have a background in mechanical engineering. I have a master's degree from UCLA. And a lot of what I focused on in my career is analysis, finite element analysis, computational fluid dynamics. And for the last 7 years, I've primarily been connected to our technical content team. A lot of, if you've ever seen videos from SolidWorks on our SolidWorks YouTube, I probably had something to do with it. Or if you've ever watched any of our live streams on our YouTube, a lot of times I'm the person who was behind the scenes. Um, but I've just recently kind of made a transition again to working more connected with customers and folks who are in our channel, our VARs. So that's enough about me. Sorry, that's pretty boring. But this is enough PowerPoint for the day. So let's just get right into SolidWorks. So I'm running SolidWorks 2024 SP1, and let's start by just talking about this simple steering mechanism that also is, a suspension mechanism. So, I mean, it's not a very complicated SolidWorks assembly. I have mates set here, so it can react as if there was a suspension system above this pillar, as well as it can react if there was turning coming from a steering box. And the cool thing about that, you can do some of the things we can do with SolidWorks is we can go beyond just 3D CAD modeling. We can simulate real life, real reality within the product as well, which is really, really cool. So the first thing that I did here was I created a motion study. So what's motion? So motion study is something, if you're familiar with rigid body dynamics, what that is I can apply motors, I can put gravity, I can add friction, and I can have my 3D CAD parts interact with each other the same way that they would in real life. Except in this module, parts aren't deforming, but they would in something like finite element analysis. In this case, we're just moving parts around based on their mass, on friction, motors. So I added a series of motors here. Let me go ahead, and first thing, you always have to add in your tools, right? So I'll add in SolidWorks Motion. And I created a motion analysis. You can see, let me just move this up a little bit. Okay, so you can see I've added a torque, some springs, added torque, added a linear motor. And if I hit play, we can see what happens here. We can see that this would be like putting this suspension system through, say you're driving, this vehicle's driving, it's going over bumps, and it's also, you're turning at the same time, kind of a worst case scenario, right? So we can also pull out real information from this. So this is a real-time plot that is showing me how much force is being applied to this tie rod, that's allowing the steering to turn back and forth as it's going over bumps. So you can see that it's, this is in values of pounds. So what we can do is we can back some information out of this, right? It's going to help me understand how much force is being applied from a motor to go through this entire process. Now, say I work for the company that builds this thing, and what I'm really worried about is, say we have a new product line coming out. We're building a set of off-road suspension parts. And this steering mechanism, this steering bracket, well, it's an old legacy part. And it's something that maybe we haven't changed. I'll go ahead and open it on its own. We'll take a look at it. And say this is something that really hasn't changed in 20 years, right? It's something that can easily be turned on a mill, or not turned on a mill, but machined, whether by hand or using a 2.5 axis CNC mill. You could pretty easily make this thing, with a couple turns of the part, and boom, you got it, a super simple part. Now, say at this company I work for, we want to try and break out into new designs. We have, like, say we have a 5-axis CNC mill that we can use. And we know we're going to need to update this steering bracket, or at least we think we do, because we know we think that with the forces that are applied in this new paradigm, this off-road vehicle, this thing might not be beefy enough. So let's go back to the previous assembly. So here's my assembly. So what I did was, I found out how much force, the maximum force that's being applied along that tie rod end, and I created a very simple study. In fact, I can build it for you as we talk here, right? So I've removed many of the parts that I don't need, because really what I'm interested in how much stress, what's the factor of safety here on this steering bracket. So let's build the FEA, the finite element analysis study, together. So the first thing that we know is that we need to add basically a ball joint between the tie rod end and this ball. Well, that's pretty easy to do in SolidWorks simulation. So that's what I'm using right now, would be part of SolidWorks Premium, where you actually have a linear static study on assemblies. You would have this capability with SolidWorks Premium or Simulation Professional, which is a tier above if you needed that. So we're going to create a local interaction, and that doesn't really mean so much. But what we're going to do is we're going to say, well, this face of this ball and the interior face of this tie rod end, well, I want to make sure that when they touch, that they create contact pressure, right? They can slip, but when force is moved from the tie rod end, it can be applied to that ball, right? So now I know that these two are connected, but they're not like glued or fused together. Cool. So the next thing we do is we want to add some simple fixtures, right? So we'll choose a fixed hinge, and this is pretty nice, right? I can choose these areas where it's bolted onto the main steering plate. I can just select these faces, and I know that it's going to act like a hinge, right? It won't be able to translate along its axis, but it will be able to rotate about the axis, right? Similar to how like a bolt works, like a shouldered bolt, how it would work in real life. Okay. Next, we want to control the movement of this tie rod. So the tie rod end, I can choose a fixture that's called on cylindrical faces. Oh, well, I already selected it. On cylindrical faces, and I can say that, well, I want that to not move off its own axis, right? It's saying here along that axis, it cannot move on the axis, but it can translate along the axis, right? So we're just basically building what are called boundary conditions in analysis here. Cool. Now we know that the end of this bracket is also connected to that steering plate, but it's not welded or glued to it. It's just kind of bolted right flush to it. So what we can do is we can create something called a virtual wall. Now, we always want to use these types of simplification techniques anytime we can, because I don't want to have to model that entire steering plate, because that's going to be it's going to take a lot more time to run the analysis. So I can create something called a virtual wall. So again, I'll create a local interaction and then choose a virtual wall. And I know I want this face is going to interfere with, I've created a plane already that's right along that face. And this face is essentially a virtual wall. And I can make that virtual wall have some sort of flexibility, like say it was steel or wood or rubber. But in this case, we're just going to make life easy. We're going to say it's totally rigid, right? So it can't penetrate that wall, but it can pull off of that wall. And that's really important. All right, now next, let's go ahead and add that force. Now, the maximum force we saw that came from our motion study was 1,500 pounds. And we know we just want to apply it right to the end of this tie rod. And I'll just go ahead and make this English, and we'll call it 1,500 pounds. So this is like a worst case scenario. Now here, we can go ahead and run it, but I'm not going to run it. This takes a few minutes to run. And I already have it ran for you. This is kind of like you could call this kind of the Martha Stewart part of the demonstration. I kind of put the unbaked cake into the oven and then pull out a baked one. That's kind of what I'm doing right now. So everything's exactly the same as we just saw, except this one I actually ran it. And let's take a look at the stress that was developed by doing this. Okay, and now we can animate it so we can get a good idea about what's really happening here, right? So a force applied on the end of the tie rod end, and as we zoom in, we can see, oh geez, that looks like a ton of flex. That looks like it's made of rubber, but I want to point something out. If we zoom in here, you'll see that I have the deformation scale set at 501. So that means it's amplifying the deformation by 500 times. So in reality, it's only just moving a little teeny tiny bit. But what this helps me do by amplifying the deformation scale just for visual purposes, this lets me understand not only did I set up the analysis right, but how is this thing actually deforming? Cool. So we can see, it's pulling away from that virtual wall that I created, but it's not going through it. So it's building up a little bit of stress here on the back of the plate. We can also see, whoops, sorry, I don't want to make you guys dizzy here with spinning this model all around. We can see it's building quite a bit of stress here at the holes that I fixed where those bolts go through. And that makes sense. Now we have a few different materials here that we're reviewing. And one of the best ways to understand if something's going to fail, if you have multiple different types of materials, is by doing understanding factor of safety. So what factor of safety just looks at is, well, what is the individual stress at that location divided by the yield strength? It's really simple. So we can see that right here in this plate, well, my minimum factor of safety is 0.994. So what does that mean? That means that that with this amount of force, it's right at that point of yielding. And as engineers, we know that yielding is something we want to stay as far away from as possible. We don't want to yield. We don't want to have permanent deformation, especially when you're talking about a part like this that's going to have many, many, many cycles. And you could end up with like serious fatigue damage, something like this. So we know from looking at this study that we're going to have to change the steering bracket. Now, maybe a few years ago, well, we just would have maybe added a bigger fillet here. Say we would have, let me go back, maybe added a thicker fillet along this edge or thickened these bracket ears. But we have this new CNC machine. We have some new capability in our shop now. And maybe it's time to break out of this very old design and maybe look for a new design, a new way to build this bracket that's not just a flat plate with two ears coming off and two holes. So SolidWorks simulation has some really cool new techniques that can help designers and engineers create, really investigate ideas almost automatically using something called generative design. So let's take a look at the space here. We're going to take a look at the design space. And we talk about like the design space of this bracket, right? So what sort of volume could this bracket consume, right? If it could consume, like how much space could it consume? Well, it could probably consume like all of this space. It could consume a much larger space. So the first thing I'm going to want to do, now just bear with me here. Well, I want to create a part, as I did here, that basically consumes the entire space that bracket would exist, right? Here are those three mounting holes we saw earlier, right? Here are the two holes that are coming down from the top, right? That actually that ball sits right in here. But in theory, that steering bracket could take on a shape this big, pretty big, right? Now we know that this probably would be just fine if we ran it. Probably is not going to fail, but it's really heavy and lots of material, unnecessary material. So in this case, what we want to create this is available in Simulation Professional, we want to use something called a topology optimization study. Okay, so what does that mean? Well, that means what we can do is we can add some boundary conditions and let the solver kind of tell us what the geometry is going to look like. I know, sounds kind of crazy. So let's go through that process. So I'm going to create a completely new study. Create a new study. Okay. And this is a topology study. So if you zoom in here, again, this you'd only have access to this if you had SolidWorks Simulation Professional or SolidWorks Simulation Premium. And we introduced the topology study analysis type. Gosh, it was probably 5 or 6 years ago. Okay, so create a new one. We'll call it topology study Phoenix SWUG. Okay. So setting it up is similar to creating a finite element analysis or an FEA study, but you'll notice there's some things that are a little different, and then the results are definitely very different. Okay, so we already have a material here. So the first thing we do is we want to just add some very simple fixtures, just like we did before. We'll go ahead and add that fixed hinge where we know this thing's going to have to be bolted to that steering plate. Okay, just like we ran that FEA study previously. All right. And we want to add those external loads. Now, the external load we're going to add before we had all those other parts, so we could just add that 1,500-pound force right on the end of that tie rod. Well, here we don't really have all those components, so we're going to kind of simulate what all those components would do using something called a distributed load or a remote load. So if I right-click external loads, I can put something called a remote load. Well, I know my remote load is going to attach to the same place that the steering ball, actually connected with an axle going down inside of it. I know it's going to connect to the same location, but I want it to be applied right in the dead center. Basically, that's where the nucleation of the force is going to be, right in the dead center of both of these two holes. So I'll choose this coordinate system that I've already created. And along that coordinate system, we can see this little arrow. This is telling me the direction of the force. So I want it to be the other way, and I want it to be 1,500 pounds. So if you see this little arrow here, maybe hard to see from where you're at, you can see that this arrow is pointed, it's pointed away, right? It's pointed that way. That was the worst case scenario, was pointed away from the part. Okay, and 1,500. So we're going to have 1,500 pounds that are basically centered on the middle here, and that's going to be translated to these two faces. And at this point, now is where things get pretty cool. So now is where we can start looking at what's our goal. Well, our goal is to find the best stiffness to weight ratio or power to weight ratio of this entire block, right? I want to reduce the mass of this thing by like 90%. And I want the study to help me understand where can I shave off material and where can I get to like basically the most optimized shape to transfer the energy from the place where the force is being applied, which is here, to the place where the force is being put back into the system, which is on these bolt holes. Okay, so I want to reduce this thing by like say 90% of the weight gone. And now I can add some things like manufacturing controls. Well, I know for sure that the locations where I've added boundary conditions and loading, well, those holes need to stay the same. They need to be there on the final product for sure. Well, automatically that preserved area is for us. But we can add other regions as well. Well, I know I want this round along the top of these bolt holes. Well, I want to keep that here, both of these faces. I want to make sure that that geometry is unaffected. I also may want to, okay, so that's a preserved region. I can also specify a thickness control, right? Say, well, I want to make sure that I don't get much thinner than, say, 3 millimeters, because that might be difficult for my machining process. Maybe thinner than 3 millimeters is just going to be, we want to keep it 3 millimeters or larger. And we can also set a maximum thickness as well. We can also select a demold direction. Okay, so say this was going to be like a part that I was going to cast, like a sand casted part. Well, I'd want to make sure that, well, sand casting actually probably is much easier than like plastic casting. So say it was a plastic cast, I want to make sure that there's no undercut, that this part could actually be plastic injection moldable. Or I can also say, well, I want to make sure that I can machine this on, say, a 3 or 4 axis machine and not have too much undercut. So I can choose a pull direction. So if I choose this edge, it's going to say, well, I know that along this edge, I don't want undercut, too much undercut under this edge. It will preserve, it'll make sure the geometry is machinable for that manufacturing constraint. And we can also identify a symmetry plane. Now, in this case, there is no symmetry plane that we can apply because you can see that this part is not symmetric. But if it were symmetric, we could do it. Okay, so this takes about 20 minutes to run. So again, I've already ran it and I'd like to show you the results. It's pretty cool. So this is, in my opinion, this is really, really, really cool stuff. So say I create a new material mass plot. And this is where we're going to see a little bit of the results. So these are the elements that the solver said, well, these places, this is where material has to be in these areas. All the stuff that doesn't, where there's no elements shaded in, it's saying that that's not necessary to be there. We can just get rid of that. This looks very different than our original bracket, right? And I can move this slider to say, well, this is the calculated weight. Well, it's saying that percentage of the original mass, if you can, maybe if you can see here. So when I slide this slider, this from heavy side to light side, this is now about 9% of the original mass, right? And it's saying that this is, and the colors go from, it's okay to remove this dark purple color, which has already been pretty much gone, due to yellow, all the way to yellow. And as I move the slider, you can see more and more of this is being cut away. So I'm actually okay with about 9%. So let's go back here. And now what I can do is I can calculate a smoothed mesh. Okay, so is this creating actual SolidWorks features? No, it is not creating SolidWorks features, but it is creating a SolidWorks solid. Go back here a little bit. You know what? I forgot to select a face to preserve it here, but now I have a little bit more meat. So what does topology optimization offer us? You're not going to use topology optimization and then immediately take this geometry and put it right on your CNC mill and cut it. What this is this gives you kind of new ideas or new directions for potentially solve new problems. That maybe this is a shape or a geometry that you would never have thought of, especially when the original geometry looked very, very different, right? So let's go make this a lot smoother. It takes a second for this mesh to actually run. And this is our optimized bracket geometry. Let's see how much it really has changed from our original. So this is what our original looked like. And now we are into this. Oops, it jumped me out of the study. I have to go back. This will take just a second. And there. So this is my optimized shape. So what would be the next thing you could do from here? Well, I can right click and I can export a smoothed mesh, right? It can either be a configuration or a completely new part file under advanced support. Now this is stuff that, you would explore this on your own, I'm sure, if you're interested, but this is where I can create a solid body or surface body or just a graphics body. And that's what's going to be, it's going to spit out, right? Say I just have a solid faceted part. Again, not a finished geometry part. And what we would do from here is we would then open that in its own. So let me just move over to this. So here's what our exported geometry looks like, right? Something like this. So I don't want to take you through all of these steps, but this is where if you would take the time and then you would build your SolidWorks parametric model using this as a template in the background, right? So it's not a magic button, but it's magic-ish. So if I hide this, or if I show this, and then hide this one. So that's our idealized geometry. And this is the idea for a new bracket. You can see that this is a full SolidWorks model, right? A full member of the SolidWorks family. I could, go through and I could change all of these features, but it's using this imported geometry as a template. You have it modeled in the background and you're designing around it, right? With this kind of, you're just designing right over it. Okay, hide that. So let's take a look at the difference, right? So we determined right from our first study with our, oops, that's the wrong button. From our first study, we found that the factor of safety was 0.994, right? Right on that ragged edge of being okay, right? And we typically, factors of safety, you typically don't want that to be 1. You want it to be about 1.5 or even 2. That factor of safety is 2 is pretty common. That means that you can double the input load and you're still not going to yield, still not going to fail. That's pretty common. So we found that our factor of safety here was 0.994. Okay, we go to our optimized shape. Well, we ran the exact same study, right? The remote load of 1500, we had our virtual wall and our hinges, all the exact same stuff. All of our, our fixed hinges, everything exactly the same when we ran this one. And this is what our stress environment looks like. It's fine. We can animate it, make sure that it's moving the right direction. Oop, I must have, let me turn on, okay. We'll turn on our deformation scale. We'll amplify that by about, we'll say 100x. So this is like 100 times the deformation scale. So as I animate this, right, we can see it deforming. Okay, that's cool. We still see a lot of the maximum stress is taking place right around the location where it's mounted to the plate, which is, again, to be expected. And let's look at our factor of safety. So our factor of safety, our minimum factor of safety, we can see here, is 1.46. That's pretty good. Almost 1.5. That's not so bad. And let's look at where that location is. So we can go into our chart options and we can show the minimum annotation. And we can see that our minimum factor of safety is right on this front bolt hole, right where it connects to the steering plate. Again, as we would expect. But that's pretty cool. We let SolidWorks topology optimization give us a new idea for a new direction for the geometry of the part. And, kind of in this, we call it the smoking gun or whatever, but what's really cool is when we start looking at things like mass properties, right? So let's take a look at our mass properties. How much does this thing weigh? So say I just want to choose my new, not the imported geometry, but my model itself, right? This weighs 197 grams, right? You see right here, almost 200 grams. If we go back to our steering bracket, and I may have to open that, the original, our legacy steering bracket here, let's see how much this weighed. This weighs, you can see it's 201 grams, 200.1 grams. So it's like the exact same weight practically. It's a difference of just a few grams. We can call that the same weight, but our new design, which has the same exact amount of material, our new design took out material from areas that was not really essential and then added that to other areas that it was essential. And now we've basically increased our strength by 50%, but there's no more material. And is this an easy case that's like kind of like a softball? Like, could most people who are engineers or designers look at this and say this can be optimized? Absolutely. But how many things do we still find there on our, say, our cars or in our dishwasher or things or any appliance that we have, old parts that look like this, that are just like that were probably designed 20 or 30 or 40 years ago, and people have said, well, we're never going to update that. It's an easy part, it works, but sometimes maybe you have to. So topology optimization really allows us as designers and engineers to give us that out of the box approach to a problem. And for those of us who are engineers, which is probably everyone in the room, and designers, problem solving, I mean, that's what, gets me up out of bed every day. I love problem solving. And this is just another tool that we can use to be more effective and build like cooler stuff. So that's about 30 minutes. Want to make sure not to go over here. Yeah, so that's what I wanted to talk about with you today. If anyone has any questions, I'd love to hear any questions. I see there's a couple things in the chat. Okay. A couple things in the chat, but if the audience has any questions, I'd love to field any questions from anybody.
Perfect. Let me see if anyone in the room has a question. In the meantime, I actually had one also.
Yeah.
I was curious on your setup. I noticed you used a virtual wall
Yeah.
instead of. I was curious the benefits of using that in the way you were using it versus like a roller slider. Not to be
Sure.
too. Hopefully, it's not too inside baseball, but
No, this is not inside baseball at all. No,
Yeah,
that's
perfect.
actually it's a great question, and it makes so let's I'll try and be as brief as I can, right, with my response, right? So how this is set up, right? So this bracket is mounted to, we can call whatever this, call it a steering plate. It's a knuckle of some sort. What do we call it here? A SEM one. Okay. So this is a knuckle of some sort. I would call this some sort of knuckle. Um, and so what a virtual wall does is it emulates the fact that it's against that wall, right? A roller slider would say that it can't do this. A roller slider means it's stuck to that wall. It can move along the plane of the wall, right? It can translate in two directions and it can rotate in one direction. So a roller slider removes 3 degrees of freedom. Um, a virtual wall says, well, this can bend like this. It can swivel, but it can't go through that wall. So you're actually reducing. It's actually a lower grade fixture, which is more realistic. So if we go to the bracket itself, and I hope I'm answering your question here. And if we look at the results, we can see here that through the process of when that force was applied, that part of that bracket is actually pulling away from that knuckle, right? A roller slider wouldn't allow it to do that. It would have to stay flat. All the elements that are touching the roller slider would stay flat instead of pulling away. So you're actually giving the part more compliance, which is more realistic. Did that answer your question? Too long-winded?
No, no, absolutely. That was perfect. I actually didn't realize the roller slider essentially adhered it to the wall also. I thought it
It does.
only allowed the movement in one direction but not the other, but that's what the wall does. So that was very helpful. Thank you.
That's right. Yeah. So yeah, the roller slider. Think of it like I don't know if when you were a kid, did you ever have like suction cups and stick them on the glass and you can kind of move the suction cup around. You can't pull the suction cup off, but it can slide along that face. That's kind of what the roller slider does. It is stuck to that face. It cannot move in or out of that face at all, only along the, but it can move along the plane.
That's super useful information. Thank you.
Sure.
And I think we did have one other question. Go ahead. Yeah, so to repeat that for everyone. So is there a reason that your starting block, your sort of start to the topology had a lot of fillets and stuff on it already versus just leaving them sharp?
No. It looks a little prettier, I guess. No. This you absolutely could run this without any fillets here. Yeah, that's not a big issue. But as we know, a lot of times in FEA, having really infinitely sharp corners, because anytime you don't fillet something or put a chamfer, if that corner sharp, and sometimes you can get something called stress concentrations there. Um, Honestly, in this case, I don't think that it would make any difference at all, because really what the solver is doing, it's a subtraction technique. And what it's doing is it's understanding the energy profile of every single element inside. And then in a serial process, it's deleting solid elements from the environment, saying this is not needed. And it starts from the easiest stuff, which would be elements out here. I'll show you the mesh so you can see it. So it'll start with elements at the furthest distance. Like this element is probably one of the first elements that is deleted from the design space, right? It's saying, don't need that. And then it just keeps deleting them until it says, oh no, I now see an energy norm within this element. And this, at least probably we need to keep this, but let's keep trying. And it's very iterative, and it keeps deleting elements until the energy pathway from that goes between force and fixture is all essential. It's a pretty cool technique. And we borrowed this from one of our sister brands called Simulia, and Simulia makes the product Abacus, which, not meaning to toot our own horn, but it is the most powerful FEA package on the planet. So,
Okay, perfect. And I did have one other question. Let me know if I'm not phrasing this correctly, but someone was wondering what's a good resources to find real world constraints basically for these types of complex problems?
real world constraints, like understanding how to create realistic boundary conditions. Is that the question?
Yeah, I think that's what we're getting at. Yep.
Well, there it takes some training. Yeah, and YouTube's a crazy place, and you can get a PhD on YouTube if you search enough. But all of that comes from a base level of training of how to use these types of tools, and also having a understanding like how the device, whatever device you're testing, how it really is connected to the rest of the world, right? I'm trying to think like of something that like an example. I'm not sure if you can like say like this microphone stand, right? Like if I wanted to understand like this bracket, right, I'd have to say, well, where is how is this connected to the rest of the world? This bracket. My camera really doesn't want to turn here. It's connected to these two parts. Okay, well, how does that move? Well, actually, the side of this bracket, these are touching these stanchions, but they're sliding across them. So it really takes like an understanding of how your part or how your assembly actually exists and moves in the real world, and all of that would come from training. Yeah,
Good to know. And it seemed like your motion study, I mean, obviously you had to understand some of it beforehand, but your motion study really seemed to help set some values and stuff for you and understand how you might need to simulate it as well, right?
that's right. Absolutely. Um, in my opinion, motion studies, you can get like sometimes that's the hardest part about running an analysis is that say wherever you work and you're like, I want to design a new bracket. Hey, how much force is being applied to this bracket? And then you talk to the engineer and they're like, I have no idea. Well, you'd have to talk to the people who build the, so uh, a lot of times information like, well, how much force do I apply to this bracket to test it in real life? Sometimes that information it isn't there. So you have to kind of keep adding components until you get to a place where now I know that, well, it's like, okay, so, some of these boundary conditions, well, I know that some of these forces that there is, as I know that some of the forces of going over, say, boulders, maybe I know that that's going to apply, 900 pounds of force when you're driving over a bump like this. It's going to apply about 900 pounds of force going straight up through the wheel. You're like, okay, cool. Well, that's a piece of information. And then you can look at, well, if someone turns a steering wheel at this angular velocity, well, that's going to apply this much linear force onto from the steering box onto the tie rod. Okay, well, I can calculate that. So you keep zooming out from the part until you actually can have tangible information and then build a study around that. And then you can back out reaction forces from motion. And it's honestly, it's one of the coolest applications for motion is be able to understand kind of your force environment or your free body force environment without actually knowing it from empirical testing. It's pretty cool. It can get you real close. And sometimes as engineers, that's kind of all we need. Sometimes like I've heard engineers saying, well, I just want to make sure that I'm in the right order of magnitude. I mean, sometimes it can be that difficult to find real information and real data. Is like, I just want to be in the right order of magnitude. I don't even care if it's, if this is 6 times too much or 6 times too less. As long as I'm close, I can design around that as a constraint.
Yeah, that's a really good point. Out of curiosity, because I haven't used Motion a lot, also can you simulate flexible materials reasonably well?
So motion is it's they call kinematics or rigid body motion. So everything in this study is assumed to be infinitely rigid, right? Parts can't bend at all. Now you can fudge the system a little bit, right? So we can create contact between groups and we can say, well, the contact here, we can understand like some elastic properties. Like say if two parts collide in motion, maybe I understand the coefficient of restitution between them, between these two parts. So that would kind of estimate, say rubber or steel or plastic, but nothing's going to actually deform here. Yeah. So that would just be like the reaction of how much force goes into the impact and deforming the part, and into the rebound. That's what you could calculate, but not say two balls hit, you wouldn't see them actually pancake out. You would just see them hit like, it'd be like pool balls, like on a pool table.
Got it. Okay, perfect. Yeah, I appreciate that.